Duty cycle control motor circuits are employed in a wide variety of components such as fuel pumps, AC blower motors, wipers, and any actual system that requires a varying motor operation. In this case, we actually see how the motor is duty cycle controlled by a driver or transistor. Again, the same principle applies. The ECM microprocessor applies a very small pulse to the actual transistor base lead. This will actually cause the transistor to become conductive. In other words, it will cause the transistor to close its circuitry and conduct electricity or electron flow between the emitter and collector leads. This electron flow, seen here flowing from negative or chassis ground through the motor and to the voltage supply line, is the actual enabler of the work being done. In other words, without the electron flow or current, the motor would actually not be able to turn. And always remember that duty cycle control circuitry has to be performed by a transistor. Relays cannot be used to duty cycle control a component, since the actual switch rate of an actual mechanical relay, it's not fast enough for this duty cycle signal to go into effect. The effective control of the component that is being connected to this duty cycle control circuit actually changes depending on the pulse of the actual duty cycle. In this particular case, we see how according to the actual length or width of the pulse, a different duty cycle rate is achieved. Here we see 50% with a specific duty cycle or open time, 25% with a narrower pulse, and again around 40% with an in-between pulse. Depending on the length or width of the pulse, that's what's going to determine the actual duty cycle. Again, duty cycle control motors are employed in a very wide arrangement of different applications. In this particular case, we see how a fuel pump motor is actually controlled. In this case, you actually see a relay applying the actual voltage source or voltage supply line to the actual motor. This doesn't mean that the motor is controlled by the actual relay. Fuel pumps are also controlled by duty cycle signals through the negative side of the circuit. In this particular case, the actual relay provides the plus or the positive side to the actual motor, and the ECM or the ECM driver provides a pulsated ground to the negative side of the motor. Again, current flows from negative to positive, and depending on the actual pulse of the actual duty cycle signal, that's what is going to determine the actual speed of the motor. Here we see a very narrow or short pulse being applied to the actual fuel pump motor, making the actual fuel pump rotate very slowly. And this you would need, for example, during an idle condition. Next, we see how the duty cycle increases and the motor actually turns faster. Remember that this is a repeatable wider pulse, and it is not repeatable here in this diagram for sake of explanation. But the longer the pulse, and now we can see that the actual fuel pump is turning even faster. The longer the pulse, the more work that the component is going to perform. Again, here we see a very short or very low duty cycle, probably corresponding in the range between 10 and 25%, and this will make, in this particular case, the fuel pump turn very slow. You will need this condition again during a non-loaded idle condition. At cruise speeds, for example, you will need maybe a 50 to 60% duty cycle for the actual fuel pump, and this we can see on the screen. And during extremely loaded conditions, or as for example when towing, you will need maybe in 75 to 90% duty cycle, making the flow of fuel through the fuel rail a lot higher. You will need this type of arrangement in any system that is actually returnless. For example, the newer types of fuel systems that do not have a return line, they rely heavily on fuel control by controlling the actual speed of the fuel pump, and this again is done through a duty cycle controlled signal. The output of the controlling circuitry is going to be determined by the width of the actual pulse that is applied to the base of the transistor that is doing the actual controlling. This pulse is modified by the microprocessor through its internal circuitry, and again the microprocessor through the actual driver, transistor driver, determines the speed of the component being controlled.